All right, the last concept we will cover this semester is going to be dealing with what are called double integrals. And this process is used when we have three-dimensional situations. And the reason I like to cover this section here is because it's a nice change or a nice reverse of the process which we did earlier with derivatives when we were working in three dimensions. Okay? In three dimensions, we worked with something called partial derivatives. And partial derivatives were used as a way of finding the rate of change of something if we keep one of the variables constant and we let the other one change. Okay? And so that's how we analyze things using derivatives in three dimensions. We kind of kept one of the variables constant, we let the other one change. Well, in double integrals or antiderivatives in three-dimensional situations, okay, we can do the same thing. We can let one of the variables stay the same or treat it like it's a constant and let the other variable change, and we can work this process in reverse. And so I want to start with just some examples here. Let's say that we've got this situation. Let's say it's x cubed times y plus y. Okay? Now, notice right away that we've got a three-dimensional function because we have x's and y's in this. And here's where this labeling at the end of the problem becomes very important. So far we've always had dx's and dy's and all these other types of things that haven't really meant a whole lot to us because we've only been working in two dimensions. So we always knew what the variable was. Well, here I can do this problem either with a dx or I can do this problem with a dy. Okay? Now, let me go ahead and start this problem with a dx, and then we'll do the same thing with a dy here in a little bit, and let me show you the difference. Okay? Now, what we're saying is we have a three-dimensional function, and we want to find the area of this object, letting x be the variable in this problem, and keeping y constant. So we kind of imagine in our mind that y is a number, like it's 10. Okay? And we're going to take the antiderivative of this equation. Okay? All right. So if I look at this first term right here, all right, let's do the second term first. If I look at the second term here, if this is just a number, what is its antiderivative? Like if that would be a 10, what would be its antiderivative? It would be 10x, wouldn't it? So if this is just a number y, what's its antiderivative? It's just this number times x, isn't it? Okay? So the antiderivative for that second piece is going to be whatever the number is times x. Okay? Now, if we come back to the first term here, okay, I've got some number times x cubed. What's the antiderivative of some number times x cubed? Well, what happens when we have numbers? Like if this was a 10 here, what would happen with that 10? Just kind of stays there, doesn't it? Okay? So the y would just stay there, and then what's the antiderivative of x cubed? X to the fourth divided by 4. Yeah. Okay? Here is, and then we put a plus constant on the end, here's the antiderivative of this term if we let x be the variable. Okay? We're just leaving y as constant, and we're letting x be the one that changes. And so this would be our answer. Now, let's contrast that with the second part to this problem. Okay, what if we let y be the variable this time and we let x be constant? Okay, well, if we come in here and look at this, take the first term here, x is a constant number. So what happens to constant numbers? They just stay there. Okay, so the x cubed just stays there. And then what's the antiderivative of our variable here? Y squared divided by 2. What's the antiderivative of this y? Y squared divided by 2, right. Okay, so same thing. And then plus a constant, okay? So you can see the obvious difference between the answers depending on if this is a problem with x being the variable or a problem with y being the variable. We get completely different results here, okay? So be really careful with this. Like I said, if you can remember to treat one of them as a constant, and as soon as you see that there's a constant, like for example, here y is a constant, just put that y down. The constant just stays there. So if you just put the y there, then take the antiderivative of the term that's got the variable on it, these really aren't too bad. Okay? All right, so there's one example. Okay? Let's look at another one here. Three plus 5y divided by the square root of x. And for right now, let's let this be a dy problem. Okay, now, the square root of x is in the denominator, although is x the variable in this problem? No. So x, this square root of x on the bottom, this is actually just a constant, isn't it? So because it's just a constant, I can leave it. I could just almost, if I just rewrite this as another problem here, I could rewrite it this way. Okay, I can kind of take that constant, just bring it out front like a fraction, and then this piece, when I get ready to take the antiderivative, this piece is not going to change. It's just a constant, so it stays there. Okay, now, what's the antiderivative of my variables? Okay, well, what's the antiderivative of 3 if y is the variable? 3y. And what's the antiderivative of 5y if y is the variable? Okay, well, the 5 is a constant, so it just stays there, and then the antiderivative for y is y squared over 2. And then again, I got a plus constant on the end here, and I'm finished off with my problem. Okay? Now, this isn't the only way to do this example, but this to me might be the easiest way to think about it. Now, maybe a question that came up as we were doing this. Okay? Why did we leave this constant go? And why on this constant, why did I tack on a y here? Why did I take the antiderivative of this thing? Why did I just kind of leave this go? Okay? Well, the difference between these two constants right here, okay? This constant is multiplied by the whole function. And whenever you have constants that are multiplied, they just kind of stay there. Okay? This constant is added to another term. And so because of the addition, that's why this needed to have its own antiderivative. Okay? So that's the difference between here. If it's addition, you need to go ahead and treat each term as an antiderivative. If it's a constant multiple, if it's multiplied, then it just kind of stays there. That's the difference between those two. Okay? All right, now again, let me just switch this problem over. What if we let this be a dx problem? Okay. Now, it appears a lot more difficult right on the surface, but again, it's really not too bad if we try to rewrite it in this form up here. Okay, so let me just rewrite this as 1 over square root of x, 3 plus 5y dx this time. All right, now this time, what is my constant? X is the variable, so y is the constant. So if y is just a number, if y is a constant, isn't this whole thing a constant then? Because if I just multiply, if I take a number and multiply it by 5 and add 3, that's just another number, isn't it? Okay? So all of this is my constant this time. So I just leave the 3 plus 5y out in front. Okay? I don't have to do anything with it because it's my constant this time. Okay? Now I need to take the antiderivative of 1 over square root of x. Probably how do I want to think about this before I try to take its antiderivative? X to which power? To the negative 1/2. Okay? Because I've got this, it's x to the 1/2 in the denominator. If I move it up to the top, it'd be x to the negative 1/2. All right, now, what's the antiderivative for x to the negative 1/2? To the 1/2 divided by 1/2, right. Okay, I add a full unit and I divide by the new power, and then I get a plus constant on the end here, and there's a little bit of work I could do to clean this up, but this is sufficient, just to get the idea across. Okay, so again, just illustrating the difference between now the problems, it becomes very important whether this is a dy or a dx, because we get completely different answers depending on which variable we're going to let change and which one we're going to force to stay the same. Okay, so there's dy and dx problems. Okay. All right, same thing can happen on these types of questions. We can have, well, let me back up to this one over here. It'll be a little bit easier to work. We can put boundaries on these as well. Okay, if I want to find out what this is from 0 to 1, okay, we have the ability to do this. We go through and we take the antiderivative with respect to x. Okay, I don't really need the plus constant on the end when we have boundaries, because that plus constant just subtracts off eventually. Okay? And now at this point, what variable should I be plugging these numbers in for? Okay? Well, I need to be plugging those in for x, because I let this be x as the variable in this problem. So when I sub in 1 for x, okay, this would become just a y in the numerator divided by 4, because this will just be 1 to the 4th. Okay? If I sub in 1 for x here, I just get a y, 1 times y. If I sub in 0 for x, in both of these spots I just end up with a 0. Okay, so minus 0 plus 0. Okay? And the difference in these types of problems is, notice that we will end up with some y's in our answer. Because we only subbed in for x, it's very possible you may end up with just y's in your answer. Okay? And in this case, if you wanted to clean this up, you could add this together. Looks like you have a full unit of y and then another 1/4. So 1 1/4 times y would be the answer to this problem. Okay? But the key is we only sub in for the variable in this problem. We don't sub in for the constant. Okay? And what this allows us to do, just allows us to let y be any number. You know, y could be 10 one problem, it could be 20 the next problem, and all I have to do to get the answer is just plug in 10 here the first time and 20 the second time. Okay? So that's the advantage of for more complicated situations. Right? So we can attach boundaries on here, fairly easily. Not a problem. Now, I talked in the beginning about this concept called double integrals. We haven't really done double integrals yet, but I wanted to get the idea across of what it means to take the derivative with respect to just one variable. Okay? What a double integral is used for, okay, it is used to find volumes. And we did some work with volumes last time, but we only did a special case of volumes, only the ones that had volume around the x-axis, only a solid of revolution. Okay? Well, there's a whole bunch of other types of volumes that we're interested in that are not around an x-axis or don't have an axis of symmetry that we can do. Okay? So we want to be able to find volumes under certain objects like this as well. Okay? And let me give an example of a situation here. Okay, I'll try to draw this out 3 dimensions. Okay? Let's say that I've just got this box, and I'm going to lay this box on the ground, and I'm going to lay it up into the corner of our room here. Okay? And let's say that the box has dimensions 2 by 3 by 4. Just a really simple box here. Okay? We'll let this be the x coordinate or the x distance. This will be the y distance, and then this will be the height or the z distance. Okay? So just a 2 by 3 by 4 box. And we all know that the volume of this box is just 2 times 3 times 4. It's just 24 cubic units. Okay? I mean, there's no reason to do an integral on this, but I'll show you the process here. Okay? All right. How we would set this up as a double integral, what would it look like? Okay? Well, let's say that the height of my box is 4. So I'll go ahead and let this be the 4 in the z direction here. The height is equal to 4. Okay? In the x direction, I want to go 2 units. And in the y direction, I want to go 3 units. Okay? So my box will look like this. Okay? Here's the box on the ground. Okay? 2 units in this direction and 3 units in this direction. Okay? And then the box is 4 units up from here. Okay? So I'm going to let this come up 4. And then try to draw this all parallel here. Let's see, this will come straight across, this will come straight across, something like this. Okay, so here's my box. Okay, 2 by 3 by 4. Okay, now when we want to set up what's called a double integral to solve this problem, we're just doing 2 antiderivatives back to back. Okay, now what we set up in here, the first part, we always just set up the value for z. Sometimes, like in this case, it's just z equals 4. The height is always 4 on my box. Other times we'll have more complicated equations. We might have equations, that maybe look like this right here, x cubed y plus y. Okay? But we just set that function, that z equals function, right in here on the inside. Okay? Now what I have to decide is, okay, what am I letting the y values do in this problem? Y values, what are the boundaries on my y values here? Okay? Well, if I look in the y direction, where am I starting for y? I'm starting at 0, and I'm going all the way out until I get to y equals what? 3. Okay, so my y values go from 0 to 3. And then my x values go from where to where? From 0 to 2. Sure. Okay? And so if I set this problem up for you, and I won't expect you to set these up as part of the course here, but if I had this set up, this is something that you should be able to calculate. It's called just a double integral. Now, when we do two integrals back to back, maybe the easiest way to think about it is to put a big bracket in here. Do the problem in brackets first, and then we will use that answer to help us do the second part. Okay, here's what I mean. All right, what's the antiderivative of 4 if I let y be the variable? Just 4y. So the antiderivative of this is 4y, and I want to calculate this from 0 to 3. So I'm going to solve this from y equals 0 to y equals 3. Okay, and we can do this in our head. If I sub in 3, and then I sub in 0, and I subtract those, what's my answer? It's 12, right? 12 minus 0 is 12. So this whole answer on the inside here came out to equal 12. Right? Now, I've done all the stuff in brackets. All I need to kind of do now is just recopy everything outside of the brackets. So now I have 0 to 2, and then a dx on the end. Okay? Now my question, well, what's the antiderivative of 12 if I let x be the variable? 12x, right. Okay, notice here we had 4y because y was the variable. Here we have 12x because x is the variable. Okay, so this equals 12x, and I want to evaluate this from 0 to 2. Okay, and again, you can do this in your head. If we sub in 2 and then we sub in 0 and subtract them, what do we get for an answer? We get 24. Okay, and that's what we said at the very beginning of this problem. We said that that volume should be 24, and it comes out to work this way. Okay? So this is what a double integral does. Okay? Is it helps us find volume. Now this one, like I said, is so easy that we would never do a double integral like this to be able to solve the problem. But if this is not just a nice little flat shape up on the top, if we don't have a nice parallel top here, if we have some weird looking shape that maybe has an equation like this, then we're not going to have a nice formula from geometry to solve it. We're going to need to be able to use a process like this. Okay? And so here's how antiderivatives come in and help us find volumes. Okay? Let's look at another example here of finding volume. Okay, make some room here. All right, our equation this time, not going to be a very difficult one again. Z equals x squared. And the x's will go from 0 to 1. And the y's will go from 0 to 4. Okay, so you can kind of imagine that we've got some type of a parabola. At least in one direction it's a parabola. I've got to, say I'm facing it this way. I've got this parabola, but I don't care about the y-coordinates, so I've got this parabola and it just keeps going into this third dimension. Okay? It's just a whole string of parabolas almost just attached together. Okay? And we want to find the volume if we let the x direction go from 0 to 1. So we're only going to take if I'm at 0, I'm only going to go to 1. I'm only going to take half the parabola, almost like I'm going to slice it right down the middle, and then I'm only going to go 4 steps in the y direction. So I don't want this thing to go off forever. I'm just going to start at 0 and go to 4. Okay? So if I had to rough sketch what this picture would look like, okay, here's my parabola going from 0 to 1. Okay? I'm just going to let it go from the origin up to 1 right up here. Okay? And then I'm going to let this go into the third dimension over here. So I'll draw another copy of it, the exact same piece. Okay? And here's what it would look like in 3 dimensions. Something like this. Kind of like a wedge almost, except for the fact that this isn't a straight line right here. It's just a parabola curve. Okay? And I want to find the volume of that object. Okay? If this has a distance of 4, I'm going from 0 to 4, and this distance over here is from 0 to 1. Okay? I want to find that volume. Okay? Well, we can set up a double integral to find this very easily. We don't have to do a lot of geometry to figure this out. Okay? Here's what it would look like. Okay? First of all, what's the equation that goes into my double integral? X squared, right, okay? Function that I have to work with is x squared, okay? Now, the order of integration really doesn't matter. You know, it doesn't matter if I put dx, dy, or dy, dx. For our problems that we're going to do, if you switch them around, you'll still get the same answer. Okay? All right. So what if I decide I'm going to let this be a dx, dy problem? Okay? What needs to be the numbers that go right here then? Has to be 0 to 1, because what I'm saying is I'm going to do the integral with x first. Okay? So I need to put my x values on the inside, and I need to put my y values on the outside. Okay? All right, now we want to actually do this calculation. Well, I start on the inside, ignoring the second integral. I'm just doing the inside one first. Okay? Just like in algebra, you start inside and work your way out. Okay, what's my antiderivative for this one? X cubed divided by 3. And then I calculate these at 0 and 1. Okay? And what's my answer when I sub those in and subtract them? Just 1/3. Okay? So all of this inside the brackets is now replaced with a 1/3. I got an answer for that piece. Okay? I drop this second one down. I drop down the dy, and now I've got just another problem that I have to calculate. Well, what's the antiderivative of 1/3 times y, or 1/3 times dy? 1/3 y. And I'm going to evaluate this from 0 to 4. And so if I sub in 4 and sub in 0 and subtract them, my answer turns out to be what? What, 4 of these would just be 4 over 3? Okay? And so the volume of this shape is 4/3. Okay? Now, just to give you a little bit of an idea of what these numbers mean as we're going through and calculating this here, okay? When we got this 1/3, you know, after we did the dx and we got the 1/3, does anyone want to take a guess? Where is 1/3 in this shape right here? What is 1/3? Yeah, exactly. If we just took the area on this end right here, just this, you know, not without going into the third dimension, if we just took the flat piece on the end, that has an area of 1/3. Okay? And then what basically happened is we came down and we ended up multiplying by 4 because we had a dimension of 4 into that y direction there, right? So that's how we came up with the 4/3. So the first step of the process basically just found the area of one of those pieces, and then the second step helped take it into the third dimension. Okay? So that's what we were doing on this calculation. Now, just to show you here, what if we switch this around? What if we go the other direction? What would it look like? Okay, so I switch my boundaries around in both, and I switch the order of integration, dy, dx this time. Okay? All right, so again, we start on the inside here. What's the antiderivative of x squared if y is the variable? Now, there's no y's on this term, is there? So this is just a constant. So this is just a number. So what's the antiderivative of a number? It's just the number times the y variable, isn't it? You know, if this was a 5, the antiderivative would be 5y. Okay? So the antiderivative here, whoops, I don't want that yet. On the inside here, the antiderivative is going to be x squared times y. And this is how we start to get all these different variables joined together here. Okay? And then I want to evaluate this from y equals 0 to y equals 4. Okay? All right, well, what's my answer here? If I sub in 4 and I sub in 0, I subtract them, I get what? Looks like 4x squared. Okay, so all of this in the inside here is 4x squared. Okay, I drop down the other antiderivative, and now I make this calculation. All right? Well, what's the antiderivative of 4x squared if x is the variable? 4x cubed divided by 3. Right, 4 just stays there because it's constant. X cubed over 3. Now I want to sub in these numbers, 0 and 1. And again, we can do this in our head because we got such nice numbers here. If I sub in 1 and then I sub in 0, I will come up with 4/3 again. Okay? So like I said, the answer will match up either way, no matter which order you do these in. Although if you had to take a preference or a choice, I would rather do this one first. You know, if I have just x's in my term, go ahead and do the dx one first. Okay? although you will get the same answer if you go the other direction. Okay? All right, questions with this? All right, good. All right, another example here. And I'll just go ahead and set this one up. All right, the function is 6x plus 2y plus 5. And the x's go from -1 to 1. Let's do the x's last this time. And the y's go from 0 to 3. All right, and this is the problem that we're interested in solving. Now, this is the equation of a plane. Okay, so this would just be, if we were actually able to go ahead and graph it and look at it, this would just be some type of a tilted plane, and we're trying to find the volume underneath of that plane. Okay, you know, maybe the side of a roof or something almost can be modeled by this. So we're going to go ahead and find the volume under this. All right, first part, dy, or the first variable is y. Okay, so let's start working through this. What's the antiderivative of 6x if y is the variable? 6xy. What's the antiderivative of 2y if y is the variable? Okay, the 2 stays there, and then there's a y squared over 2. And then what's the antiderivative of 5? 5y. And we're going to evaluate this at 0 and at 3. Okay? Now, this problem in the book didn't necessarily say I had to go in this order, but I purposely picked the y to go in the middle, and my reason is because I saw it had a 0 for one of its numbers. Okay? It just makes it a little bit easier if you can do your zeros on the inside. You have less numbers to number crunch in the middle. Okay? All right, so if I sub in 3 for y into all these spots, what do I come up with? Here I get a what? 18x. If I sub in 3 here, look like 9, because the 2's will cancel, so just 3 squared, 9. And then over here, if I sub in 3, I get 15. Okay? And I could clean this up and make it 18x plus 24. Okay? So 18x plus 24 goes in for the brackets up here. Okay? I simplified it. I did all my substitution and cleaned it up. Now 18x plus 24 is the next antiderivative that I need to take. Drop down the first integral, drop down the dx. Okay? Now I'm ready to go ahead and do this problem. What's the antiderivative of 18x, x being the variable? 18x squared over 2, antiderivative for 24, 24x. 24x. And I want to evaluate this from -1 to 1. Okay? Now, I talked the other day about doing some little shortcut tricks. You know, if it goes from -1 to 1, sometimes you can change this to a 0 and multiply it by 2. We talked about that little trick. But be careful, because that only works if you have a nice symmetric graph, you know, from the left side to the right side. And do we know if this is a symmetric graph? Well, we don't know that for sure. So I probably don't want to make this change unless if I graph this and see that I have symmetry from left to right. Now, in this example, I definitely won't have symmetry because this is just a straight line. And so the left side will not reflect over to the right side. Okay? So I need to leave these the same. I can't just do a trick and sub in a 0 here. Okay. So I just need to sub in these numbers here. Well, we can clean that up and make it a 9 here. Okay, if I sub in 1, what do I get for a total? Okay, if I sub in 1, it looks like 9 plus 24, so 33. If I sub in -1, this is 9 minus 24. 9 minus 24. -15. Okay? And then when I go ahead and do this, now remember, this was a -15, but I still do subtraction in between them because I still take the value I get for the first one minus the value I get for the second one. Okay? So this is actually 33 plus 15, so it looks like the volume underneath of this plane happens to be 48 cubic units. Okay? So just be a little careful with that, especially the subtracting negative down here. Okay? But otherwise, it looks pretty good here. All right, questions with any of those? Okay, another example. Okay, we just did that one here. Okay, this one is already set up for us. 0 to 4, 0 to x. Square root of x times the square root of y, dy dx. All right, now, there are also times when it would be necessary for us to not only have numbers in all these spots, but there would also be times when we might want this to be a variable in the spot, okay, as opposed to a number on this side. Now, what's the difference? Why would we have, what would the situation look like if we have all numbers? What would it look like if we have variables? Okay? Well, just to rough sketch this real quickly here. Okay? If I have numbers in both of these spots, what I'm saying is that I'm letting this base piece, whatever shape it is, a box or some weird looking shape, the base is rectangular. It's a perfect rectangle. The y's go from 0 to 3, the x's go from -1 to 1. Okay? So I just have a nice perfect rectangle along the bottom. That's what this situation is over here. Okay? If I let one of these be a variable, what it would mean is I'm going to let the x's go from 0 to 4, and I'm going to let the y's just go from 0 to x. I'm not going to let them go to a specific number. I'm going to let them go to whatever the x value is. Okay? And if I was to graph this, if x is 4, then y is also 4. Here's what the bottom would look like. Instead of it being just a nice rectangular piece on the bottom, I would have some type of a triangular piece on this one. Because what I'm saying is if x only goes to 2, I only want the y value to go to 2. If x goes to 3, the y value can only go to 3, and so forth. Okay? So all this is doing is it's just changing the shape of the base as opposed to being rectangular to something else. Okay? But we still go through and do the process exactly the same way. Okay? All right, we start on the inside here. We start with dy integral. Okay? All right, what's the antiderivative? Well, let me say it this way. What happens to the square root of x? It stays there because it's constant. It's multiplied, so it just stays there, right? So square root of x doesn't go anywhere. Okay, now what's the antiderivative of the square root of y if y is the variable? To the 1.5 divided by 1.5, sure. Okay, it was to the 1/2, so I just add a full unit, divide by the new number. Okay, and I want to evaluate this from y equals 0 to y equals x. Okay, so we go ahead and start subbing things in here. If I sub in an x, okay, I'm going to rewrite this as x to the 1/2. This is x to the 1.5 divided by 1.5. All I did was I just subbed in an x wherever I see a y. Okay? All right, so that's the first piece. Now I subtract what I get when I sub in 0 for y, but what will I get when I sub in 0? I'll get 0, right? 0 to this power is 0, divided by and times other stuff is still 0. Okay, so this is just a 0 right here. Okay, now let's clean this up here a little bit. Okay, if I have, just off to the side, if I had x squared times x cubed, what would be the answer? X to the 5th. I just add those exponents together. Okay, so if I add these exponents together, I get what? X squared, right? Okay, so this simplifies to x squared divided by 1.5. Okay, so all of this on the inside here, it looks fairly complicated to start with, but now it's just x squared over 1.5. Okay, now I drop down the second antiderivative, the second integral. Okay, now what's the antiderivative of x squared divided by 1.5? Okay, well first of all, what happens with the 1.5? It just stays there. Anything that's multiplied or divided just stays there. It doesn't go. Okay, so I'll have, I could write it this way, 1 over 1.5. I could write it as a fraction. Now what's the antiderivative of this? X cubed over 3. And I'm going to evaluate this from 0 to 4. Okay, sub in 4 here. Now this isn't quite the nicest number here, but whatever this happens to be, okay, when I sub in 4, if I sub in 0, I again just get 0, so I'm subtracting 0. Okay, so whatever this happens to come out to be as an answer, that's the volume underneath of this shape, square root of x times square root of y. Okay, but again, the difference in this problem was we just had an x up here in the boundaries, although it really doesn't change a whole lot in terms of our process. The only difference, instead of subbing in a number here for y, we're just subbing in a variable like x. Okay, so this allows us to solve a completely different set of problems here now. Okay. All right, next example here. Okay, so we'll just have a rectangular bottom this time, from 0 to 3 and then from 4 to 5. But the function's going to be a little harder to work with this time. And dy dx. Okay. Now, usually when we have a situation like this, where it's a complicated function, we may want to consider even rewriting it in the other order. You know, I like to usually try to do the more complicated piece first, get it out of the way before the problem gets too messy here. Okay? And as I look at this problem, I only have one y in the problem, so I don't think the dy piece is going to be too bad to work with. Okay? However, the x part is going to be more of a problem because I have x's inside the radical and then another one outside the radical. Okay? So what I'm going to do is I'm going to switch this problem around. Okay? I'm going to let us do the x's first, and then we'll do the y's second. Okay? So I'm just switching the order of integration on this problem. Let's do the hard part first, and then we'll come back and get the other one later. Okay, what will I have to do in this problem to solve this for dx? Oh, question?
Yeah, does that, you talked earlier about trying to use the zeros on the inside?
Yeah.
Relate?
More coincidence on this. I was more interested or more concerned about the fact that I have multiple x's in this one as opposed to 0, but that's also an added benefit, yeah. Yeah, it will make it a little easier. All right, what will I have to use to do this antiderivative? When we have multiple x's like this, and I can't just distribute through and do some algebra, what technique from earlier will I have to use? Okay, this is going to have to be a substitution, right? Okay, and that's why I said this one is going to get a little bit more complicated. Okay, so in my substitution, I've already got two different variables here. Well, now I'm going to have to introduce that u. I'm going to have to let there be another variable show up here. So I'm going to let u equal what in this substitution? X squared plus 3y, right. Let it equal the complicated piece. And then what is du? And remember, I'm concerned about x here. So what's the derivative of this thing if I let x be the variable? 2x dx, right. Okay. This has a derivative of 0 because there's no x's in it. Okay. Now let's go back and let's try to substitute and re-look at this problem here. Okay, so I'm just looking at the inner integral for right now. Okay, all right, this piece right here will change over to what? Square root of u. Yeah, I'm just replacing all the part under the square root with a u. Okay, now the only thing I haven't subbed for yet is the x and the dx, and that's really close to what I have here. Okay, what do I need to do to make it match up perfectly? Divide off the 2. Sure, so I'm going to divide both sides by 2 so that I can replace x dx, I can replace it with du divided by 2. Or another way of saying that, I can put the 1/2 here and I can put the du right here. Okay, maybe a little easier way to think about it. Okay, now, the other thing is though, once I make a substitution to a different variable, okay, I also have to change my boundaries. Okay? So I need to take these values of x and I need to convert them to values of u because that's my variable in here now. Okay? So what if I take x equals 0 and sub it in here? What do I get? I get a 3y, right? 0 plus 3y. So the lower boundary is now u equals 3y. And what's the upper boundary if I sub in a 3 here? Nine plus 3y, right. Okay, so now I have converted these back, I've converted them into values of u. Okay, all right, now let's go ahead and take this antiderivative. Okay, the 1/2 just stays there. What's the antiderivative of square root of u? U to the which power? 1.5 divided by 1.5, right. Just add a full unit, divide by the new power. Okay, and I need to evaluate this from 3y up to 9 plus 3y. Okay. All right. Now, I want to kind of clean this up here a little bit before we get into this too far. If I have a 1/2 and I divide by 1.5, let's get that as a single number here. Okay. What is it? I have a 0.5 divided by 1.5. How many 0.5s go into 1.5? 3s, right? So this is 1/3. Okay? So this is all just a 1/3. Make it a little bit easier for me to work with here. Okay? All right, so now we start doing our substitution. Okay, we've got 1/3, 9 plus 3y to the 1.5 minus 1/3, 3y to the 1.5. All I'm doing is I'm just substituting in those values wherever I see the u there. Okay? This mess right here, this is what goes in for the bracket. Okay? That's our inner integral here. It took us a little while to get there, but this is our answer. Okay? Now I drop down the second one, and we need to make the calculation on it. Okay? So from 4 to 5, what do we come up with here? Okay? We need to make a little more room. Okay. Now, as I look at this first part, I'm now taking the antiderivative with y, so I don't have to do anything, too fancy here. Okay. The 1/3 will just stay there. Okay. What's the antiderivative of this? Okay, I've got something to the 1.5. So let's think about it this way. Okay, what happens when we have something to the 1.5? The something gets raised to the what? 2.5 divided by 2.5. Sure. Okay, I just had to up the power by 1 and divide by the new number. Now, the only thing is here, do I have a chain rule on the inside here? Yeah, what is it? It's a 3, isn't it? Okay, so in the normal chain rule, I'd be multiplying by 3, but what do I need to do up here because we're going the other direction? I have to divide by 3, right? Okay, we've seen some examples kind of like that before. Now, dividing by 3, I'm just going to stick that 3 down here in the denominator with the other number. Okay? All right, minus. Now, let's do something very similar with this one right here. What's its antiderivative? Yep, 1/3. 3y is now to the what? To the 2.5 divided by 2.5, and then what's my chain rule on the inside? Again, it's a 3, so I would have to divide off by 3 again. Sure. Okay? And now I am ready to make the actual substitution at the end, y equals 5 and y equals 4 from my antiderivative, and I would plug those numbers in, and I'll just stop at this point. I mean, it's just a matter of punching it in your calculator and seeing what the result would be. Okay? So this problem got to be a little messy for 2 reasons. One, and the major reason, because we had this substitution in the middle here. Okay? And it was already complicated enough with 2 variables, and now we went ahead and had to introduce a 3rd variable to make it work. So that made this problem a lot more difficult than what I'll be expecting you to do for an exam, but this is, again, just the types of problems that we now can solve. Okay? All right, we'll see you next time.